All right, so welcome back. Let's see where I was. I think we were looking at finding the limit to this rational function, and we decided to capture the model and simplify it and then insert the infinity, the appropriate infinity based on the limit statement, and then come up with an answer. So, and again, like I said, this fits case 3 down here when the degree of the numerator is larger than the degree of the denominator. Okay, just more practice. Let's look at this problem right here. All right, the limit as x approaches negative infinity of the same function. All right, well, what we can say is that this limit is going to be approximated, I guess you can say, by the limit of the end behavior model. Okay, so let's see if I can kind of clean that up there. That's not good. Oops. Let's come back down here. Where am I? Here I am. Okay. Perhaps I need to select this object. Okay. All right. And, okay. Let's space that again. And pick that up. Can I just select that up here? There we go. All right. Well, I guess we'll just deal with that. All right. So the limit here. Oh, goodness. The limit as x approaches negative infinity. Let's capture the model again. Like I said, we have 3x to the 4th. It's your leading term. I don't know what's going on. Why does that? Why is that coming off? In the denominator, we have, why is this doing this? X cubed again. Okay, simplifying. Results in 3x. Inserting negative infinity, so the answer to this limit question is negative infinity. Why is that? Why is it going pink? All right, looking at problem number 4. Okay, same procedure right here. Let's just kind of study this. In the past, if you were asked the end behavior, you would see 6 is greater than 2. And in this case, 6 is greater than 2. You're looking down here going, well, that's case 3. Okay, so my answer is going to be a slant asymptote, or not horizontal. And so in pre-cal, you would have done long division, okay, and figured out what the end behavior asymptote was by long division looking at the quotient. Well, in calculus, we just want to describe the end behavior, if it's infinity or negative infinity, without actually having to find it. Okay, so what we're going to do here then is we're going to use the model to help us predict the end behavior. So the limit as x approaches infinity, so this is approximately, okay. We've got 5x to the 6th. Down here we have 2x squared. All right, so take a look at this. We can simplify it. So we have 5/2 x to the 4th. Okay, if you just think about, again, you can just insert infinity, evaluate it, or think about what this graph looks like. And if you remember earlier in the lesson, we looked at polynomial functions. All of these, when your degree of the numerator is less than the degree of the denominator, in all of these cases, you're going to end up with a polynomial function. Well, think about the linear function 3x. Okay, well, a positive slope. As x takes on large values, the graph's going up, so my answer should be positive infinity. Okay, so you can kind of think of it that way. Okay, so 3x, as x goes to negative infinity with this positive slope, my y values are coming from down below, so that's negative infinity. Okay, same thing here. When you simplify, either insert the infinity, do the calculations, or think about a 4th degree function, positive coefficient, looks like a w, both ends are up, So whether you put in infinity, take it to the fourth power, multiply by 5 halves, you're going to get positive infinity. All right, let's look at this limit problem, okay? You're asked to find end behavior of this rational function. Here's a strategy. Approximate it using the model. Show this work. Simplify. Use your reasoning skills, okay, to think about when you insert negative infinity, what effect that has on the answer. Well, that's going to be a positive infinity to the fourth power. Okay, so my answer is going to be positive infinity. Or think again of what the general shape of this polynomial model is. Well, it looks like a W, so both ends up, so both my limits, whether I go to positive or negative infinity, should be positive infinity. So this is just the calculus way to use notation to describe something that you guys have been studying for the last couple of years, end behavior. And the way you've been studying end behavior of rational functions, okay, is by looking at a comparison of the degrees of the numerator and denominator. And you can fall back to that if you want to. If you're one of those students that's comfortable with the comparison here, wonderful. Continue doing that for calculus, okay? And that will help you answer the limit question, okay? All right. Okay. Oh, goodness. Okay. But if you weren't one of those students that was comfortable with this information right here, and maybe now you can see these problems right here, okay, as end behavior questions and have something else to fall back onto to answer. Okay, if you want to see this as capturing the model, simplifying, thinking about what this graph looks like, or actually just inserting the positive or negative infinity, either way, just trying to give you another option. But certainly what I want you guys to take away from this, I want you guys to understand that this notation, okay, as x approaches infinity or negative infinity, embedded in a limit question, okay, that's referring to the topic of end behavior. And how we proceed is different than, say, what we've been doing in the past as far as x approaches a particular c value. Okay, so that's kind of what I wanted you to take away from this lesson is the end behavior notation of rational functions. This might be a good idea, or this might be a good time for you guys to turn the worksheet over, the notes over, look at all the questions on the back. I have a mixture there for you guys. Okay. I know it's taken so long. So it's just not acting right. Okay. This might be a good time for you to turn the worksheet over. Look at the problems on the back. Okay, if you kind of look at the graphs, okay, if you're not familiar with the graphs, you might want to pick up your calculator and see if you can produce these same kind of graphs that I did. Okay, exploring them a little more detail on your calculator. I think you'll be okay with most of them. I think you see that on 4, there would be 2 vertical asymptotes, one at x equals 2 and one at x equals negative 2. And I think you might see that this particular area right here, this, for some reason, this calculator graphed the vertical asymptote at x equals negative 2, but not at x equals 2. So just know that this is not part of the graph. It is the asymptote that was graphed on the screen. Okay. 5, there are 2 vertical asymptotes at where your denominator equals 0. You could solve those if need be. Okay, if you looked at 6 real quick, okay, you see that the degree of the numerator is greater than the degree of the denominator. So that indicates you don't have a horizontal asymptote like these 2 graphs, that there's a slant asymptote. And that's why this graph looks the way it does. And if you thought about it, based on what we just did previous, if you looked at say the model, this is approximately 2x cubed, the highest exponent 3 up here, x squared down here. Just watch out. Sometimes they don't lead off. Okay. They might be rearranged, but this is definitely the highest exponent. If you simplify, you're going to end up with 2x. So think about what 2x looks like. Okay. So our slant asymptote would look something like this. So that's why the graph looks the way it does. Okay. And it looks like there appears to be some vertical asymptotes in here too. So, you know, even though I gave you the graph here, you still need to know a little bit about the graph to help you answer some of these questions. But this might be a good time for you guys to see how many of these you can answer. Notice I have a mixture of review questions as X approaches some C values here, but then I also threw in some end behavior questions too. Okay, so you might want to answer as many of these as you can, and we can discuss those certainly tomorrow. All right, I'll see you then.